My name is Zha Ruiqi, a student researcher from Shenzhen College of International Education. Today, I am excited to present my project on motion control of manipulator robots. This work focuses on developing a precise control system for robotic arms, combining the theoretical principles with hands-on engineering. Let me walk you through my objectives, methodologies, and key findings. This project designs and tests a PID-controlled motor system to understand the precise motion control from theory to real-world implementation. Let me introduce the key findings and steps of my projects. My foundational research began by tracing the evolution of robotic arm control from the early hydraulic robotic arms in the 1950s industrial robots installed at the General Motor for car manufacture to the modern closed-loop systems for robotic arm control in medical surgery and space exploration. The research focuses on designing and optimizing a PID-controlled robotic arm for precise motion control, combining the robotic engineering with control theory. I began by studying the mathematical and logical foundations of control system, analyzing how theoretical equations for feedback loops and error corrections are physically implemented through electrical circuits. This theoretical grounding provided me with essential insights to the control system before moving on to any practical work. With the principle understood, I then transitioned to the electrical component implementation phase. Here, I designed and built electrical circuits to test different control methods, specifically proportional, proportional integral, and full PID control. Through systematic testing, I observed how each component uniquely impacts the system. The proportional term affects the reaction speed, the integral term eliminates steady-state error, and the derivative term is able to reduce overshooting. These comparisons gave me tangible insights into control system design. And finally, to validate the control system in the real world, I simplified the problem of controlling a robotic arm to single motor control. On the breadboard prototype, I implemented a system where rotating an input knob would make the motor mirror the exact rotation angle. This hands-on test not only demonstrates the position control in action, but also reveal practical challenges like signal noise and response latency. This was my first breadboard version of the PID control. The wiring picks up interference and causing these unstable jumps, and the response has continuous oscillations when I alter the set point due to the bad tuning of the system. This prototype helped me to diagnose issues that occur in the real world. This graph shows how this motor controller prototype responded. The motor was supposed to reach the target smoothly, but instead, as you can see, it is oscillating. The voltage keeps going up and down. The system did not stabilize. These wobbles and delays happened because the breadboard wiring picked up electrical noise, and the coefficients of the PID control were not fine-tuned. So I decided to move the circuit to a custom PCB, where the motor response is much faster and more consistently. Here's the PCB motor controller. Rotating the knob of the potentiometer sets the target position, and watch how the motor responds instantly, and look at the difference. Even with rapid changes, the motor stays locked on target. This project gave me 3 really valuable takeaways. First, I developed a much more practical understanding of the PID control, seeing how the theory actually works when applied to real-world circuits. Secondly, I gained hands-on experience with circuit design and simulation tools that brought these concepts to life. But most importantly, I strengthened the problem-solving approach, learning how to systematically identify issues, test potential solutions, and implement improvements. These skills have been incredibly useful for bridging the gap between textbook knowledge and actual engineering work. Thank you very much.